B, one of the questions was number 3 that people asked about, and it's asking what are the quartiles. So if you had a set of a datum, I'll just make up some numbers: 1, 2, 3, 4, 5, 5, 6, 7, 8. Um, the middle number, the median, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. So the middle number is 5, and that's Q2. Half the data is below it, half the data is above it. So it splits it into halves. Q0 is the smallest number. And Q4 is the largest number. And if you split the lower half in half, so 1, 2, 3, 4, since that was the middle number, we're going to not use that one. And so it'd be between 2 and 3. We call it 2.5. And that would be the Q1. And what the quartile, why did we have the quar? That means quarter. We're splitting the data into 4 equal parts, from the lowest to the first quarter, from the first quarter to the second quarter to the third quarter. Since we don't count the 5, we would go these 4, it'd be between 6 and 7. 6.5 would be the third quartile. The boundary between the third and the fourth quartile is another quarter of the data, roughly. So quartiles are just dividing the data up into 4 roughly equal groups, and the boundaries between the quartiles are these 5 numbers, sometimes called the Tukey 5-number summary. Tukey is the name of the person who was working with this concept. 5. It says, describe the process of calculating standard deviation. So you find the mean, and then you see how far the mean is. Each number in the data set is from the mean. So how far each data point is from the mean. 3, square that. 4, add these up. 5, if you're doing a sample, divide by. N minus 1, if you're doing the population, divide by n. And then 6, you would take the square root. Okay, so they said now do this for this sample. They said we have 2, 3, 4, 4, and 6. There's 1, 2, 3, 4, 5 numbers. We add them up. 6 and 4 is 10. 2, 3, and 4 is 9. So we got 19 divided by 1, 2, 3, 4, 5 numbers. So the mean is, 5 goes in there, 3.8. Then we take each number, 2, and subtract 3.8. 3 subtract 3.8. 4 subtract 3.8 twice, because we got that one twice. And so we're going to take it times 2. And 6 minus 3.8. This one we have once. This we have once. And this we have once. But before we do that, we square each of these. So we're going to square that, square that, square that, square that, multiply by these, and get some numbers here. So 2 minus 3.8 is minus 1.8. Squared is, it's not minus 3.8, it's positive 3.24 because the negative times the negative is positive. I should have put the parentheses around that. Let's do the next one. 3 minus 3.8 is minus 0.8, so I should go parentheses, minus 0.8, close parentheses, squared. Oh, come on, get down here. Parentheses, minus 0.8, close parentheses, squared is 0.64. I have to take it times 1, but that doesn't change anything. Now the next one, 4 minus 3.8 is 0.2 squared, and I have 2 of those, so that's 0.08. And then I have 6 minus 3.8, which is 2.2 squared, and I only have 1 of those, so that's 4.84. So then I add these up. 4 and 4 and 4 is 12, plus 8 is 20, carry the 2. 4 and 6 is 10, 18, carry the 1, 7, 8. So I've found the mean. I calculated how far apart they are by subtracting. I squared those and then added them all up. 1 of those, 2 of those, and 1 of those, added them up, got this. Then I divide by n minus 1, so 8.80 divided by, I have 5 data points, so I divide by 4, which is 2.2, because this is a sample, and then I take the square root. The square root of 2.2 is 1.48. And that's the standard deviation. And what it means, then they asked one more question on number 5. They said, what if all the data points were the same? Like if it was 4, 4, 4, 4, 4, then the mean would be 4. And if I subtract the mean of 4 from each one of these, I get 0, so there'd be no variance. So the standard deviation would be 0. So a really small standard deviation means all the numbers are really close together. A big standard deviation means it's really spread out. Okay? That's number 5. And then we have 29 was asked for. So I'm going to go to 29. And that problem says, an auto transmission manufacturer receives ball bearings and shipment. It says supplier A has a bunch, supplier B. Find the mean and standard deviation of each data set. So now I'm going to use the calculator to do that. I'm going to go through the same process. Well, not quite the same process. I'm going to let the calculator go through that process. So I'm going to go up on list 1, clear it, come down, go to list 2, clear it, come down. List 1, I'm going to put supplier A, which was 16.25, 16.27, 16.29, 16.31, 16.34, 16.37, 16.41. The second supplier was 16.19. Only one. 16.22, 16.28, 16.34, 16.39, 16.42, and 16.44. And now I can get the mean and the standard deviation by simply going stat, calculate the one variable statistics on list 1, and calculate that. The mean for the first one was 16.32, that's the mean. Sometimes written with an X with a bar over it, sometimes written with that symbol, Greek M. So the mean of the first data set's that. Stat, calculate the one variable statistics on list 2. And that comes out to have a mean of 16.32, actually 33. I wonder what the other one was. It might have been the same. Let's go back to that. It was 16.32 exactly. So they're pretty close to the same mean. Now, this first one, the standard deviation of the sample is 0.056. The standard deviation on the second one was 0.098. So this one, there's more variance. There's more spread in the answers. So it's more likely that these will go out beyond the specifications needed. So the standard deviation, so if I just look at the data again, you can see this one has a low of 1.9 and a high of 16.44. This one has the highest is 16.41 and the lowest is 16.25. So this has more spread. It's more spread out than this one. So that's what the standard deviation is telling us. So if we were to draw a curve on this one, the spread on this one is more like this, and this one is more like that. Now, if you're trying to meet standards and have quality control, you want suppliers that can give you a narrower band. Now, the next thing it says draw a box plot for each data set. Oh, that's a lot of work. So second, quit. So stat, calculate the one variable statistics on list 2. So I need the quartiles, the 5 quartiles. So everything's between 16 and 17. In fact, I think they're all between 16 and 16.5, so I'm going to put 16.5 there. And so this is the second data set, and I have the minimum as 16.9, 16.19. So 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got a little spread out here. More like that. So if the low is 16 point, not 1, but 19. So the low is there for the second data set. The first quartile is 16.22, which is here. And then the median is 16.34. 16.34 is about here. The upper quartile, or the third Q, is at 16.42. And then the max is 16.44. Okay, so the center is pretty wide here. Now let's take a look at list 1, the first supplier. So stat, calculate the one variable statistics on list 1, and it comes up with the lowest one is 16.25, then 16.27, which is right close to that, and then 16.31 is right about there, and then 16.37 is right about there, and then 16.41 is right about there. So you can see how list 2 is spread out, as the standard deviation says, is spread out more than these. That one's got a less of a spread on it. And then it says part C, what percentage of the ball bearings from each supplier meet the specifications? Now they said it had to be supposed to be 16.30 with a tolerance of plus or minus 0.1. So they need them to be somewhere 16.2 to 16.4. Now if we go back and look at the lists here, list 1, 16.25 is okay, 27 is okay, 29 is okay, 31 is okay, 34 is okay, 37 is okay, but 41 is too big. So the first list only has one of the, how many are there? 1, 2, 3, 4, 7 of them, is there? 1, 2, 3, 4, 6, 7. Yes, 7 of them. 1 out of 7 doesn't meet it. 6 out of 7 meet the specification. You can change that to percentage. That's what they wanted. I'll do that in a sec here. How many of the second list don't meet the specifications? 1.9 is too small, but 2.2 is okay, 2.8 is okay, 3.4 is okay, 3.9 is okay, 4.2 and 4.4 are too big. So there are 3 that don't make it. So there are 4 that do make it. So if you were running a factory and you had to make things work here, I don't want that. Second quit, that's what I want. So 6 divided by 7 is 85% of these bearings would work, 86%. And on the other one, only 4 out of 7, which is 51%, are good enough. So you'd be throwing away nearly half of 57%. You'd be throwing away almost a little less than half of the bearings because they don't meet your specifications, don't have the quality control you need. So that's what they wanted you to do for 29.